try to get you caught up when we can. But you'll take the test with everyone else, which is next Wednesday. All right. All right. Okay. So I have 6 problems that I'd like to try to do today. I don't know if you get them done. So we're going to try to work on it. I thought yesterday we had a reasonably productive discussion of formal definitions and limits. And so we're going to look at this a little bit today. Let's start off with number 13. This is our problem. Who is it? Austin. Okay. Page 91. Okay. Number 13.
Let the coordinates, let P, the coordinates X, Y.
13. 13.
Oh, 13, sorry.
Okay. And a lot of the books are messed up. It has X times A. You should say X is less than A. But his is right. His is right. Anyone else is messed up? Over there on the very far hand side, next time I call you guys, the books are good. Mine's a little bit over crazy. Anyway, let's write this function down. It's called the pulse function. E of A comma B X of X is, go ahead.
Okay, equals H, times X, H of X minus A minus H of X minus B equals, in brackets,
each has to find
0 when X is less than A, 1 when X is greater than or equal to A and less than B, and 0 when X is greater than or equal to B.
I'm interested that it equals 1 when it is A, but it's 0 when it is B. I was thinking it might be the same both ways. Let's see if we can understand it. We gotta somewhere, what's the heavy side function? What's H of X? What's H of X? We have to write down, no, it's
in brackets 1 when X is greater than or equal to 0, and 0 when X is less than 0.
Okay, so H of X is easily graphed. It's just 1 and 0. Base returns 1 or 0. If it's a positive number, 0 returns 1. If it's a negative number, it returns 0. Okay. Now, what's going on here is we're plugging in A, B. So let's imagine A is less than B. All right. And here's A, and here's B. Now, when we plug in, when we have a number here that's less than A, then the X is less than A. Do you understand? You guys follow it right here, the X value is less than A. So, if I have something less than A and I subtract A, do I get a positive or a negative? I get a negative. What's H of a negative? H of a negative is 0. So this returns 0. So I'm going to just put it right here. X is less than A. I'm just going to have it between, and then I'm going to have it greater. I'll deal with the equal parts again. When X is less than A, this is 0. And if X is less than A and I subtract B from it, what do we get? Positive or negative? So that's 0 also. And so the answer is 0. Let's have it bigger than B. Let's come out here. X is bigger than B. It's a really big number. Okay, awesome. X is bigger than B. So if X is bigger than B, B minus A, positive or negative?
Positive.
So H of that is
1.
1. I'm here, X is bigger than B. And I'm bigger than B, so is this positive or negative?
Positive.
So I get
1.
So the answer altogether is
0.
0. Now, if I'm between A and B, when we subtract A, it's positive, so this is 1. When we subtract B, it's negative, so this is 0, and that's where we get 1. Now, when it equals A, A minus A is 0. A minus A is 0. So that returns 1. And X minus B is negative, so it returns 0. So that's working. But when we're equal to B, this is is clearly positive, and this is still equal to b minus b, so it's returning 1 as well, and that's why when greater than equal to b leaves us with the 0 at that spot. So you guys agree with that? And so the net effect for this function is that in these values it returns 0, in these values it returns 0, and these values it return 1. So the function looks like here, open circle, it climbs to 1, closed circle, open circle again, and then it drops back. So this was just my work to try to understand what was going on. And you understand why it's called a pulse function now? It pulses upwards from A to B. What a cool little function. It's a function defined on another function, and it's called a pulse function. Sketch a graph of the pulse function. A. We did it. We sketched a graph of the pulse function. You guys follow how that works? Now, obviously, I could have just followed this, taken this and written it down, and it would have been much faster, but I was trying to convince myself that those were the same. We do that a lot in this class. In fact, we have to always be willing to say convincingly. And I'm not going to be able to do that all the time. There's going to be some spots where I was going to do it. But at least we can recognize what we've been able to convince ourselves of and whatnot. I'm convinced this is legitimate. I'm convinced this is legitimate for that explanation based on this definition. Anyone have an issue with it? Okay, Austin, part B.
Part B, find the following limits.
Okay, first one.
Limit of p of x as x pushes a from the right.
What's the answer?
1.
Okay, keep going. Next one.
Limit of p as x pushes a from the left. 0.
Any disagreement? Speak up if you have a disagreement. Keep going.
Limit of p as x pushes b from the right. 0. 0. And same thing as x pushes b from the left. 1.
Okay, you guys good with that? Part C.
This is the continuity of the pulse function. It's not continuous.
Okay, it's not continuous at what spot?
At points A and B.
Not continuous at x is A and x is B, but it's continuous everywhere else.
Yes.
So it's continuous everywhere, but at x equals A and x equals B. Okay. So I don't think it's fair in this case to say it's not continuous. Actually, it's fair to say it's not continuous. It's not. But it's probably more helpful to say it's continuous everywhere but where x is A and x is B. Of course, then again, when we have the graph of it, the goal, the graph shows everything. It shows all the limits. Part C. Is there part D?
Yeah. Y is u of x equal to 1 over b minus a times p of x, called the unit pulse function.
Okay. So we have u of x, which is 1 over b minus a times p of, now I didn't do it right. What is it?
1 minus b minus a times p of x, called the unit p a, like with a b, something a b.
Okay. Alright, I got it. I know why it is. Why is that called unit function? What's it called? Unit?
The unit pulse function.
Unit pulse function. Why is it called the unit pulse function? Let me just give you an example right here. If A was 10, B was 32. Okay? This would be at 10, this would be at 32. This would still be up at 1. But if I did this, the unit, it probably should have AB there, right? Did it? Did it have an AB there? No, it should.
No, it did not.
It should have. 1032 of x is 1 over 32 minus 10 p of 1032x. It looks exactly like that function before. At 10 it jumps, and at 32 it jumps back. And so it looks like this, except for what? What's different between this and that? I did that wrong. This should have been, this should have been. So now it's looking the same. But what's different? Jimmy? The y value. The y value isn't 1 here. The y value is 1 over 22. Why is this one called the unit pulse function? The unit circle has a radius of 1. Unit multipliers are 1. They make 1. Why is this called the unit pulse function? The area beneath the curve is 1. What's the area beneath that curve?
Most likely 1.
No, that one. What is it? Count it up.
Oh, sorry.
It's 22. It's 22 wide, 1 high. The area is 22. What's the area under this curve?
1.
1. It's guaranteed to be 1 because we have a length of b minus a, and now we have a height of 1 over b minus a. Area equals 1. That's why it's called the unit pulse function. Now, I think the author should have written u of a comma b. Why? Why? Because it corresponds with this. It depends. The unit function depends on the a and b. And in effect, this is a multivariable function. It's dependent on not only the x values, but on the a and b. But the a and b are parameters. So we put them out here. Because we set a and b, and then we work the function with a single variable x. Okay? Very cool. Questions on 13? Nice little review of a few different things. Nothing too difficult, but a pretty cool problem. Okay, next one, number 9. Nick, 9.
Consider the graphs of the 4 functions g sub 1, g sub 2, g sub 3, and g sub 4.
Okay? Alright, so I'm going to do a quick sketch of them. One. And you might want to be looking in your textbook, know exactly what's going on. G sub 2. G sub 3, and G sub 4. Okay, keep going.
For the given condition of the function f, which of the graphs could be the graph of f? A, the limit of x approaches 2 of f of x is equal to 3.
Okay, go ahead. Read A again.
The limit as x approaches 2 of f of x equals 3.
Now, if you look at these graphs, every single time, this key spot is 2 comma 3. This is 2 comma 3. This is 2 comma 3. Which one is this? This is 2 comma 3 up here. Okay, I think I have that right. Okay, which ones work where the limit of the graph is x approaches 2 is 3?
G sub 1 and G sub 4.
G sub 1, G sub 4. What about G sub 3?
It doesn't work because they both approach 2 different values from the 90 value.
And then it doesn't exist. And what's wrong with G sub 2?
The limit is 2.
Limit is 2 instead of 3. This is at 2 comma 2. So I agree with that. Part B?
F is continuous at 2.
F is continuous at x equals 2. Go.
G sub 1.
Any disagreements? The only one that's continuous at 2 is G sub 1. Part C?
The limit as x approaches 2 from the left of f of x equals 3.
X approaches 2 from the left. Of f of x is 3. Go.
G sub 1, G sub 3, and G sub 4.
Any disagreement? In D?
There's only C.
Let me see. Is there more to 9 or is it finished it?
That's all.
Yeah, that easy, huh? That's a pretty easy problem. Pretty rare to get problem solving problem that easy. You guys know that on, let's see, the test is next Friday, so Tuesday after that. The test is Wednesday the 4th. So the Friday is 6th. Chapter 1 problem solving stuff. And I think it says on your assignment sheet you have to do 5 of the 6. So we're going to do 14 right now. And you have to do 5 of the other 6. And they'll need that for the next night. Okay? It's a 40-point assignment. That's the challenge of this course, business problem solving ones. They're pretty good. And, help each other out, but, don't let people mooch off. Just don't let people mooch off you. Only help people out who are also contributing to the discussion. Otherwise, you're not helping their academic development if you're just mooching off you. All right, I'm actually going to erase this and try to keep 14 on the front. In 14, I have difficulty with every year. I think I'm going to refer to my notes. And we're gonna skip that for a second, and we're gonna go to exercises 9 and 10 and come back to it. Okay? And what we're doing is something called delta epsilon proofs. Okay, we're doing delta epsilon proofs. One of the more difficult things in a serious college calculus course, most college calculus courses finesse this now. It's not on the AP curriculum, A, B, or BC. Even the idea of delta epsilon is not there. But we got into yesterday. You guys did some graphs of the relationship between delta and epsilon. And so we're going to see if we can do some of these proofs. The first one is trivial. The second one, little bit tough. I think I'll do one in between. It's a little bit, I'll just do an executed one. It's a little bit easier. But here we go. Let's do number 10. Trivial. We're trying to prove that the limit as x approaches 5 of 9 is something. We're supposed to find the limit and then use the epsilon delta or delta epsilon proof to prove that the limit is true. Now, this is a ridiculously easy problem. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our graph. F of x is always 9. 1, 2, 3, 4, 5. What is the limit as x approaches 5 of 9? 9. The y-x approaching is 9. Okay? Now, our definition, I'm going to put the definition right here. The limit as x approaches c of f of x is number L if and only if for all epsilon greater than 0, arbitrarily small. I don't need to write that, but it's helpful. For every single possible epsilon someone picks, no matter how small they pick it, there exists a delta greater than 0 such that if I get within the distance from x to c is less than delta, then I'm not at c. The distance isn't 0, then I'm less than delta away, implies that the distance between f of x and L is less than the epsilon they gave us. Yields implies sometimes we just put in there. Okay? That's how we define the limit. So here's our proof. This is the definition I'm going to base the proof on. If you don't agree with this definition, then we're stuck. I mean, this is what we're building our proof on. They asked us to do a delta epsilon proof. So we're doing it on this definition. It's going to be really simple. Proof. Let epsilon greater than 0, arbitrarily small, be given. So someone gave us an epsilon. We don't know what it is. we're going to call it epsilon. It stands for the number they gave us. No matter how small it was, it's a positive number and it's really, really tiny. Now, in this case, let's say they pick this as the epsilon right here. Now, this is not the scale. So there's my epsilon, that tiny little distance up and down. They're giving me basically a tolerance for how close the distance between f of x and L has to be. They're giving me a tolerance. What can my delta be? What's my delta need to be? Because we know that for this to be the limit, there has to be a delta such that when I'm within delta of 3, because we're dealing with, what am I talking about? 5. C is 5. When I'm within delta 5, I'm within epsilon. Well, the fact is I can know the A. This doesn't matter. So the most convenient number is 1. We will let delta equal 1. Notice that f of x equals 9 for all x. Therefore, f of x equals 9 for all x elements of for all x where 0 is less than x minus 5 less than 1. In other words, between 4 and 6. Thus, f of x minus L is 9 minus 9 is 0, which is less than epsilon in my proof stuff. I had to show that there was a delta where as long as I was within delta of 5, the distance from the y value to the limit was less than epsilon. And of course, the distance is 0 because it's always 0 away from that. Trivial. Okay? Now I'm going to erase some things. Okay? I'm going to do another one. It's not in the book. It's something a little bit more reasonable. Okay? And so we will let, I'm erasing, I'm changing the problem. No need to change that. But I'm going to go with limit as x approaches, let's go 8 of the cube root of x 2. Okay? Now if I draw the cube root of x, looks like this. You guys agree this is true? The limit of x approaches 8 and the cube root of x is 2. And let's prove it. Let's prove it. So, someone's assigning an epsilon right here. It could be really, really small. Okay? Okay, now I'm just being really honest. I'm not a super expert at this. I have been at times. I'm not remembering how to do it. I might struggle with this. I might not even do this right. We'll end up looking at a couple of the solution manual and we'll get these right. I'm trying to expose to these delta epsilon proofs. For those of you major mathematics, this will be about one of the hardest parts of the undergraduate experience is delta epsilon proofs. Another hard part is abstract algebra. You can handle it. Okay? A lot of the other parts of the major math are just not that difficult, exception. But this is one of the hard ones. It's tricky to do this. So we're going to let delta be, so what I'm going to choose is, I'm going to let it be epsilon cubed. I think that's what I need to do. I need to let delta be epsilon cubed. Whatever number they give me, I'm just going to cube it. Okay? And it seems to me like I'm getting in super close compared to where I need to be. Because if they make it 1/100th, when you cube 1/100th, you have 1 million. Okay? And you're super, super close. So I'm coming in and I'm letting delta be 1 million. And I'm going to say, notice, now I'm having all sorts of trouble. So I'm going to work backwards. This is how you learn to do proofs in geometry. When you have trouble, you work forward, you work backward, you try to make it meet in the middle. So at the very end, I'm trying to get the fact that what we have implies that, I'm just going to write it more classically with the arrow, is 0 is less than x minus c, let's see in this case, 8, right? That when this is less than delta, we get f of x minus my limit 2 is less than epsilon. My proof is given. So am I done? No, I haven't convinced that this is legit, right? I just wrote the final answer. I knew that's where I needed to get. I got to get to that though. I want to show that the absolute value of x minus 8 less than delta yields the cube root of x minus 2 is less than epsilon. Okay? And I don't think I've done it right. I think I picked something that's difficult to do. I was thinking it was easy, but let's try a little bit though. Okay, one thing that we know we have is we have 0 is less than x minus 8 is less than delta. This equals epsilon cubed. Follow? X minus 8 is epsilon cubed. Okay? Do you realize that x minus 8 factors into x minus 2 cube root of x minus 2 times the cube root of x squared plus 2 cube roots of x plus 4. X minus 8 factors into the cube root of x minus 2 times this business. You agree? Which we know is less than epsilon cubed. You know, based on the shape of this thing, it seems like the shape, I'm just gonna go with something easier. I'm just gonna let delta be epsilon. I'm just gonna make it a lot easier. I let delta be epsilon. It came back. I let delta be epsilon itself. I think I can do that the way it's shaped. Okay? And now I'm really close because x minus 8, you know, we know that we pick the delta. So we know that the distance from x to 8 is less than delta, or greater than 0, which means the distance from x to 8 is less than epsilon. But the distance to x minus 8 is this. Do you agree with this? Now, what is this kind of number right here? Okay, positive or negative? Okay, when we're, you know, sometimes what we do this. We let it be the minimum of epsilon 1. Okay, so we make sure it's at least as small as 1. Okay, so and x minus 8 is less than 1. So x is between 6 and 8. You follow? I'm saying that my delta, if they pick a tiny epsilon, I know I'm really close to 8. But if they pick a bigger epsilon, I'm going to pick it as 1. Okay, something small. It's the minimum of that. It's smaller than epsilon if epsilon's bigger than 1, right? And what I'm doing is I'm saying this is between 6 and 8. So if this is from 6 to 8, isn't this a positive number? Isn't this a positive number? And I'm adding 4. 6 is less than x is less than 8 yields that the cube root of x squared plus 2 cube root of x plus 4 is certainly greater than 4.
7 and 9.
I should have said 7 and 9. Thank you, Chair. One away from 8. Number's 8, so one away. If I'm between 7 and 9, isn't this number greater than 4? Okay, so isn't this is, okay, so epsilon is greater than that. This is greater than that. Do you agree? Because we're multiplying by 4. So this is bigger than that. You guys follow? Well, I've done it. So I have this then. I have this is true. Because of this stuff, we know that this is greater than 4. So this is bigger than that. And now I have the fact that if you pick a number, a delta 0 is less than x minus 8 is less than delta, then it yields that this is less than epsilon. And I've done the proof. I've done the proof. We weren't surprised here. We knew if we picked something by the geometry, if we picked something as small as epsilon, the way it was shaped, because it's shaped this way, if I come that distance as a square to the side, clearly all these y values are within epsilon. They're way within inside epsilon of what we need to do, right? Clearly way inside. But that's the kind of trickery that you have to do to do these delta epsilon proofs. Okay? It is hard. Now let's go to number 10. And that's I'm gonna pull it right out of the solution manual. So I'm gonna give you the author's solution number, I should say number 9. We're doing exercise 9. Someone read the limit that we're supposed to do here.
The limit of x approaches to x squared minus 2.
And what's that going to be?
1.
1. So now we're doing the proof. So let epsilon greater than 0 arbitrarily small be given. We're going to let delta equal. Okay, now I'm going to see what they did here. I'm going to see what they did in the follow through. Review exercise number 9. Okay, they do this on the side. They say we need, this is where I do a lot of proofs, we need x squared minus 3, f of x minus 1 to be less than epsilon when I'm within delta of 2, right? That's what we need. You guys follow that? They notice that this is x squared minus 4. They notice that this is x plus 2, x minus 2. Do you see how this is starting to match up now? See how this is starting to match up? When we're really close to the number 2, isn't this going to be positive? So here's how they write it. Okay? They have some more there, but that's just as they're figuring out. So they say, okay, that delta, they do it really as the minimum of 1 and epsilon over 3. I think they're making epsilon over 3 in a clever way to make it come out more exactly. Just a clever way with experience. Actually, they have epsilon over 5. My bad writing. Where in the world is the 5 from? Okay, so therefore, when we have the distance from x to 2 is less than delta, which is epsilon over 5, it yields And what they do is they break this up into x minus 2, they multiply by x plus 2, okay, multiply by x plus 2, and you multiply both sides by x plus 2, and this is, actually, they do this, let's skip a step. They say this is less than epsilon divided by x plus 2. This is the recognition they make. Epsilon over 5 needs to be less than epsilon over x plus 2.
Well, where does that 5 come from?
Okay, they picked a number that was going to be smaller than what happens when I'm within 1 of the number 2. So if I'm within 1 of 2, this is basically going to be, okay, let's see this right. If delta equals 1, would yield x is an element
I guess
of
it can be caused, it can be away.
2 comma 1 comma 3.
Like in 3.
3 to 5.
9 minus 3 is 6.
Right.
6 is the 5 is the difference.
With delta being less than or equal to 1, x is certainly going to be between 1 and 3. Because delta is the distance away from 2, right? And so if my distance is less than 1, the distance from 2 on the number line puts it from 1 to 3. Now if x is from 1 to 3, adding 2 to it makes it from 3 to 5. And so epsilon over 5 is less than epsilon over 3, epsilon over 4, epsilon over, we're not quite getting 5. Should you agree that this is true? Okay, now once they've done that, they're multiplying this by the adjective value of x plus 2, and they multiply the epsilon over the adjective value of x plus 2 by x plus 2. I don't like my notation, my handwriting, so I'm going to change this to try to make it clearer. They're multiplying both sides by the adjective value of x plus 2. Okay, let's back up. Very clever. It's a backwards thinking that you get good at when you do lots of these problems, which you might do in a certain math class over weeks. So we're saying we need to prove that when if this yields this, that's what we need to prove. We need to show that this yields that. That was the definition. Do I need to review that definition, or are you guys good on that? You don't need to, it says, basically, you need to prove that when the x's distance from C is less than delta, it forces the y's distance from L to be less than epsilon. That's the gist of a limit proof. So here's the x's distance from 2 is less than delta from 2. And this is the y, x squared minus 3's distance from the limit L, 1, has to be less than epsilon. We're trying to go from here to here. Well, we have, if this is true, we assign delta to be epsilon over 5. Because we're within 1, we know that epsilon over 5 is less than epsilon over the adjective value of x plus 2. Now, if that's true, I can put the intermediate step in there. We had x minus 2 is less than epsilon over the adjective value of x plus 2. This is less than that. Now I multiply by the adjective value of x plus 5. And now on the left side, this is the same as that. And this, of course, is epsilon. But what's x squared minus 4 the same as? X squared minus 3 minus 1 is less than epsilon, which is what we were to prove. QED, that which was to be demonstrated. Proof done. QED, that which was to be demonstrated. Follow? Number 14, problem solving 14, we'll go over it tomorrow. It's in your notes. I've worked it out a couple of different years. I've handwritten it out carefully. It's in your notes. I'll put it on the board and we'll just talk it through. It's pretty tough. It's one of the problem solving ones. It's pretty tough. you are supposed to, for homework, do 7 and do 9. You might have no trouble doing those now, but you might end up skipping one because you can skip a few problems based on the way I do it. Okay? I'm gonna stop class. There's only 5 minutes left. You guys can be working on homework. I know you have some due tomorrow, right? Today. Okay?